So in this video, let's try solving a little kind of kinematic style problem where we have something moving in a circle. So in this case, we're going to have an insect sitting on a record. He's sitting 5 centimeters away from the center of the record, and then I turn the record player on and the record starts rotating, and it starts accelerating faster and faster until it gets up to, you know, whatever the maximum speed is for the record player, which we're not going to worry about. So let's assume that this happens at a constant, that the insect has a constant tangential acceleration, 0.5 meters per second squared. How long will it take before the insect makes one complete revolution and comes back to the same point as where he started? Okay, so how are you going to approach this? There's actually a few different ways you could approach this. Let me show you first in this video a simple-minded method of how you can approach it, which will work. It's not necessarily the ideal method, but it works. That is, let's imagine this to be a good old-fashioned one-dimensional kinematic equation style problem. Yes, bizarrely, the one dimension in my kinematic equation is no longer a straight line. It's actually folded into a circle. So basically what I'm doing is taking one-dimensional kinematics along a line, and I'm just wrapping that line around into a circle and now applying kinematic equations to that circle, which is a little bit squirrely. And you might wonder how far I can push that analogy, but the way I'll do it here should work. So anyway, let's try it. So because I'm going to do that, the first thing I need to do here is set my mind on the kinematic equation framework, which, remember, when you're solving a kinematic equation style problem, what you want to do is identify the initial and final states, start listing off your known variables and your unknown, and then choose one of the kinematic equations and apply it. So I have here, I don't think I need to really draw the initial and final states here. They're actually the same. The insect is sitting at a certain location on the record. In between the initial and final states, he makes one rotation. He ends up back at the same place where he started. So let's think about, what do we know in terms of kinematic variables? So I'm given here in the question a constant tangential acceleration, 0.5 meters per square second. I am going to treat that as the object's acceleration. Now, this is pretty dubious, you might think, because this is actually not the object's acceleration. In fact, let me just put that this is the object's tangential acceleration, because I don't want to be confusing about that. The object, the insect also has a centripetal acceleration, which we don't yet know the value of. This is only the tangential acceleration, but because the centripetal acceleration only tells us that he's moving on a circle, it's not actually going to affect the kinematics of how he moves, as long as we put in the fact that he's moving in a circle elsewhere. So we're going to treat that like the acceleration in kinematic equations. So what else do we know here? We know that the record starts from rest, so that tells me his initial velocity. And we also know that he makes one complete rotation, so that's telling me his delta x. Now again, this is a little bit squirrely because technically his displacement is actually 0 for this process because he ends up at the same place as where he started. But because I'm doing this one-dimensionally along the perimeter of the circle, I have to take into account the fact that he made a complete loop. So I'm going to put in the delta x as 2 pi r, the circumference of the circle, which again is slightly weird, but will work. So it's 2 pi times, he's 5 centimeters away from the center of the circle, so that means that's his radius, 5 centimeters. So 2 pi times 0.05 is 2 times pi times 0.05 is 0.314. Oh yeah, I could have figured that out in my head. Just pi divided by 10. Okay. So there's 3 known kinematic variables, so I feel good about this. Now let's see, what's it asking for? How long will it take? That's t as my unknown. So now I can apply a kinematic equation to this. Let me see, looking at my 4 variables, I think the appropriate equation is this one, dot plus 1/2 at squared. So this will be 0.314 equals 0 plus 1/2 times 0.5 times t squared is my unknown. So I'm going to have 0.314 times 2, divide by 0.5, take the square root, and I'll get t equals 1.12 seconds. So I got my answer. So this is kind of a stupid way to do this problem. I pointed out as we went several things that were a little bit sketchy about how I applied one-dimensional kinematics to this problem. It actually works doing it this way, and that is the correct answer. There's a better way to approach it, which I will show you in a future video. This is attempting to solve it using the methods that you already know from earlier in the